program, the lecture from Galileo to James Webb Space Telescope, third March of Astronomy by Professor Kembhavi. Now today, 2 days ago, we celebrated Republic Day, and this year's Republic Day started with the good omen of having 2 physicists on the list of Padma awardees. And we hope the trend continues in spite of having the pause button pressed on the other awards. It is a bright morning in Chandigarh, Panchkula and Mohali, and I welcome today's speaker, Professor Kembhavi, and the guest of honor, Professor Bagla. Professor Bagla himself is, in a way, host as well, being a life member of. I also welcome a group of school students joining today from Pataudi, which is a small town in Haryana, and also another group of students from Peck. I don't see that they have not joined, but in anticipation, I welcome them. I welcome all of you who have joined us this morning. And with this, I request Professor Arun Grover to give his opening remarks. Professor Grover.
Thank you, Kia. So good morning, all. I am particularly excited about welcoming all of you on the occasion of an online expository lecture at SPSCI Forum by an eminent astronomer, Professor Ajit Kembhavi, whom I first met as a fellow PhD student as we enrolled to do PhD in Graduate School of Physics of Tata Institute of Fundamental Research more than 50 years ago in August of 1972. We have been in close contact with each other since then. Internationally renowned cosmologist and theoretical astrophysicist, Professor Jayant Narlikar returned from Cambridge to join as Professor of Physics at TIFR few months after our graduate courses had commenced. Professor Narlikar gave an advanced graduate school course on relativity and cosmology for our senior batch in January of 1973. However, all of us from our batch also enrolled for the course delivered by Professor Narlikar. Many students from first and second year wanted to join Professor Narlikar for PhD, but Professor Narlikar chose just 2 of them, and one of them was Ajit Kembhavi. Ajit has remained as a student, collaborator, and colleague of Professor Narlikar ever since then. And by virtue of it, I have also enjoyed the patronage and affection of Professor Jayant Narlikar and his spouse, mathematician Dr. Mangala Narlikar. When Professor Narlikar proposed the creation of Inter-University Center for Astronomy and Astrophysics on the campus of Pune University in 1987, he selected 2 younger colleagues, namely Dr. Ajit Kembhavi from TIFR and Dr. Naresh Dadich from Pune University as the founder faculty members of IUCAA along with him. IUCAA progressed to become a pioneering inter-university center in the UGC system in just about 15 years' time. After the superannuation of Professor Narlikar as founder director of IUCAA, Naresh Dadich and Ajit Kembhavi performed the responsibilities of the subsequent directors of IUCAA for 1 term each. Ajit had loved teaching even when he was a PhD student along with us at TIFR. He used to go back to teach at St. Xavier's College in South Bombay in his spare time. From his mentor Jayant, Ajit learned the art of public communication on topics of science, in particular in astronomy, quantum physics, and in the later years, data science. Ajit carved a niche for himself as an observational astronomer, institution builder, promoter of interinstitutional collaborations, library and information science expert, promoter and nurturer of science-based programs of Space Commission, proposer of India's participation in global mega astronomical instruments, gravitational wave research, etc. As Vice Chancellor of Punjab University, I had an opportunity to initiate Chandigarh Region Innovation and Knowledge Cluster to promote inter-institutional collaborations. I implemented many ideas and thoughts I had learned from the experience of IUCAA and other inter-institutional centers. Professor Kembhavi, after his superannuation as a director of IUCAA, created Pune Knowledge Cluster. Pune Knowledge Cluster and the Delhi Cluster, DRIIV, are emerging as role models for other clusters in India. I am personally looking forward to listen to Ajit's public lecture titled From Galileo to James Webb Space Telescope, the Forward of Astronomy. We are grateful to Ajit that he readily accepted to deliver today's talk. Astronomy is very close to the heart. It's a passion with Mr. DharamVir, the president of SPSTI. And Jasjeet Bagla also has been helping the astronomy programs of SPSTI. So I'm very happy that we have both Ajit and Jasjeet with us. With this, I can conclude. Back to Kia. Thank you very much.
Thank you, Professor Grover. I now request Dr. Smriti Mahajan of IISER to introduce today's guest of honor. Dr. Smriti herself works in the very glamorous area of observational astrophysics. Over to you, Smriti.
Good morning, all. Thank you, ma'am. It is indeed my pleasure today to introduce Professor Jasjeet Singh Bagla. Professor Bagla is an eminent astrophysicist and cosmologist in the country. He worked on his PhD thesis with the late Professor Thanu Padmanabhan at IUCAA, followed by postdoctoral positions of varying durations at the Institute of Astronomy in Cambridge, England, and then Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. He then joined the Harish Chandra Research Institute in Allahabad as a faculty, where he spent almost 11 years prior to joining IISER Mohali in 2010, where he continues to serve as a professor of physics in addition to numerous other administrative roles. From my personal observations of him in the last 9 years that I've spent at IISER Mohali, I can easily say that Professor Bagla is not just a very passionate teacher, but an excellent administrator, a quality we will all agree rarely is observed even amongst the best. He's equally interested in science and science education and has greatly contributed to both on various platforms. His current research interests encompass both theory and observations, varying from simulations of H1 content in galaxies to gravitational lensing of gravitational waves to models of dark energy and dark matter. So now it is with honor and it's my pleasure that I pass on the baton to Professor Bagla.
Thank you, Dr. Smriti. Professor Bagla, please start your address.
Thank you, KRG and DharamVir and Professor Grover for the kind invitation, and also to Smriti for the very, very kind and flattering introduction. Anyway, the focus today is on Professor Ajit Kembhavi and the talk that he will be giving. I first met Ajit back in 1988, I believe, when he and T.P. Prabhu came to Delhi University to do a short workshop on essentially what was then the CCD revolution in observational astronomy, which these two and Professor Kurinder Pal Singh were essentially pioneering in India, bringing new technology and trying to make sure that Indian astronomy does not lag behind. And this passion for making things accessible is something which I have seen in him as a founding member of IUCAA and as a Dean of Visitors Program over there. He essentially set up the associate program and made sure that it flourished. And along with the associate program, he also made sure that not only IUCAA welcomed associates to its own campus, but associates also got facilities at their own respective campuses so that their own students could work better and be more productive. Later on, he went on to contribute enormously by making sure that universities were able to subscribe to journals, making sure that UGC provided this facility, and also online access to journals from own desks. Ajit has continued to contribute to this through things like virtual observatory and virtual many initiatives, including India's participation in the excuse me for the disturbance. We are actually traveling from IIT Mandi to IISER Mohali, and we stopped on the way to join the meeting. So someone decided to anyway, coming back to the topic, I hope we'll be listening about wonderful achievements of various international agencies which have contributed to building the JWST, which is a marvel not only for astronomy, but also in terms of robotics and engineering, and how it is going to revolutionize our understanding of the universe. I pass the baton back to you, Ajit. Thank you.
Thank you very much, Professor Bagla. I now request Professor Harvinder Kaur Jassal, again from IISER Mohali, a well-known astronomer herself, and also an active participant in Women in Science programs. So Professor Jassal is requested to introduce today's speaker. Harvinder, please.
Thank you, KG. It's a pleasure. Ajit needs no introduction, and already Professor Grover and Jasjeet have summarized quite a lot of what I was saying, but nevertheless, for people who joined in late, Ajit did his PhD with JVN at TIFR in theoretical work, cosmological singularities. And later he went on to do a postdoc at Cambridge University with Martin Rees, and came back to TIFR as a faculty member. And he was one of the founding members of IUCAA, and he moved to Pune when IUCAA was constituted. And he's been there, and during his tenure there, he was Dean of Visitors Programs, as I just mentioned. And he also was instrumental in a very well-developed associate program. And lots of PhD students also visited at that time, including one of sometimes me visited to avail of the facilities which were available to all the people who were visiting from various universities. In IUCAA, he also constituted and established the virtual observatory program, and while he was a faculty member there. And later, when he became the director of IUCAA in 2009, he was instrumental in Indian participation in SALT, TMT, and LIGO international collaboration programs. And he made sure that India was an active participant in these international collaborations. He has very honors and awards to his credit, but I must mention that he was a president of the Astronomical Society of India. And currently he is the vice president of International Astronomical Union. He has given various public lectures, both including in Marathi also. He's also written a book in Marathi, co-authored with JVN and Bagla. And his public outreach work has also gone on to basically encourage other public outreach people. And Ajit and Asha constituted the Zubin Kembhavi Award, which is given alternate years to either public outreach or observational work. So without further ado, I would just say the topic is very interesting, and it will give a history of how we started from Galileo and come to the new JWST collaboration kind of telescopes that we have here. Ajit, looking forward to your talk. Thank you.
Thank you, Harvinder. I can only say wow to that kind of introduction. And now I request Professor Kembhavi to start his talk.
Thank you very much. But before I start, may I please share my screen? Can you see my screen?
Yes, sir, we can see.
Okay, all right. So thank you very much, Arun Gobar and STPI for inviting me to give this talk. I've been hearing about STPI and these programs from Arun for a very long time. And I'm very glad to be a part of it this morning. Now, there have been multiple introductions which are a bit embarrassing, but in spite of that, when Arun first introduced me, he forgot to say one thing, that we first met in 1972. Subsequently, our parents also met each other, those who are 3 parents, and the in-laws, and then they became friends. And then our children became friends. Each of us has one son, and they worked on the same project for Microsoft, but one from Hyderabad and other from Seattle. Now they are both in different occupations. They same IT thing, different companies, but they continue to be there. And their grandchildren are close friends. Our grandchildren are close friends. So we are already talking about 4 generations, and let's hope that continues into the future. Great. So I'm going to talk to you about beginning with the work of Galileo and going on to the James Webb Telescope, Space Telescope. So this has been a 400-year-long march of astronomy. There's substantial astronomy before that too. But what I'm interested in today is to see how technology makes completely new ideas and new investigations possible. New investigations, and through that you get the new ideas, or your new ideas which you put into reality by building a new telescope. So I'll focus on the technology, and then it's very interesting. And then at some of the jumps into new technology, I will show one result at least, which was very significant and which is easy to understand. Because there are all sorts of technical results which keep coming out, but something which appeals to absolutely everyone. That would be my focus today. So Galileo Galilei was a very great personality, and I can't see some of my own screen because all these sort of things are there, but you can see the date here, 1564 to 1642. So here is presumably on the terrace of the observatory in Pisa. I've been to that same observatory some years ago. And then he was the first one to use the telescope. He did not invent the telescope. He just used it to look at the sky. And his first telescopes can be seen now in the museum in Florence, which is very close to Pisa. And then Galileo made the most marvelous discoveries. Right, so here, what you see here is a close-up of sunspots. And some of you may have read recently that sunspots are visible to the naked eye. And then Galileo was the first one to observe them with a telescope. You can't look at the sun directly, but you would have got a mirror through the image through the telescope on the wall. And then now you see, what I'm showing you on the screen is a modern close-up of sunspots. But then you see here on the right, Galileo's drawing of sunspots, and you see how closely they resemble each other. So Galileo started his observations of the sun in 1612 and made notes, made diagrams, which are all available today. And each one of these discoveries was very momentous, because you see that according to the then prevailing theology, the sun was a very perfect object. It could not have any blemishes on it. So this was strike one against Galileo. He discovered sunspots. Now for us, he was a great scientist, but for the other people there at the time, he was not a very nice person going against theology. Then you can see here from in Galileo's original handwriting and his diagrams, what is shown here is the planet Jupiter, and then you can see these satellites around it. He found these tiny objects, which you can see in this modern picture. 4 of the Galilean, these are called the Galilean satellites, because now we know that there are many, many more. But Io, Europa, Ganymede, and Callisto. Right, so he discovered that these objects were going around Jupiter, and then that therefore realized that they are the moons of Jupiter. So which was strike two against him. It was a great strike for astronomy, but it was against him because everything in the heaven was supposed to be going around the Earth. So now he gives you direct and substantial evidence that there are objects which are actually going around Jupiter. Then he pointed his telescope to the Milky Way and discovered stars in it. He went on and on like that. But perhaps his best discovery has to do with this object here, which looks like the half moon, but is actually Venus. So when Galileo observed the planet through his telescope, he found that it has phases just like the moon does. And so you can see here a modern set of pictures taken with a small telescope, where you can see that you've got the relatively full, almost full Venus, and then it goes on waning, and here you see the crescent Venus. And a very interesting thing that you see is that as you go from full Venus to the crescent Venus, the size of Venus has increased substantially. So Galileo, it was not his job just to observe and to leave it, but to draw inferences from it, which is what observations are always about. And then Galileo concluded from these observations that it is the heliocentric theory which is correct. Because if Venus and Earth, if Venus and Sun were both going around the Earth, rather than the Earth and Venus going around the Sun, then you would not be able to see the phases in this form. Okay, so as usual, you have this sketch by Galileo, and you can see clearly as you go from the full Venus to the crescent Venus, you can see the increase in size, just like we observe it today. So Galileo was a very talented person. He did all sorts of things during lifetime. So he had to make a living in addition to doing astronomical observations. He did that through giving tuitions. Okay, but then he also had other expertise, like he worked out the theory of projectiles so that large guns could be used effectively during the war. He was a great physicist. He developed the concept of inertia. And then his principle of inertia became the basis later of Einstein's special theory of relativity. And then Galileo is supposed to have gone up the Tower of Pisa and dropped a light object and a heavy object and showed that they both fall with the same time to the ground. This is known as the equivalence principle, and it was a cornerstone for Einstein's development of the general theory of relativity. So you see that both special theory and general theory came from the thoughts of Galileo. I mean, thoughts of Galileo were very conducive to the development of these theories by Einstein. So people continued to use hand-held telescopes for a long time. And then they also developed the technology. So here is a telescope developed by William Herschel, who was actually German, but he carried out his astronomical observations from Britain, which is where he was resident. And there is a place called Slav near Heathrow Airport, where he had put up this telescope. And I believe, if I remember correctly, Arun and I have been to Indian eating establishments in Slav in our time. And there was a vast Indian population there. And he put this telescope there, which was 48-inch diameter primary mirror. Because the most important part of the telescope is the mirror, which collects, this was not a primary mirror, primary lens, I should say, which actually collects the, I think it has the light. And because they used lenses, it was a refracting telescope, it had very long focal length. So this was 40-foot long focal length. And it was the largest telescope in the world for over 50 years. So now you'd imagine that he made very substantial discoveries with this telescope. But actually from my reading, which was not very deep, I find that he did not really discover very much with it. And one big factor there, of course, was the weather in Slav. And particularly, the English weather is always bad for astronomy. And then in those days, of course, it was much worse. And you could hardly observe it at all. And you can see here that were very cumbersome kind of observations. But of course, Herschel contributed greatly to astronomy because he was the first one to map in some manner the shape of a galaxy. And he put the sun at the center of the galaxy, but he did not know in those days that there was a lot of dust in the galaxy which warped the vision. He also discovered the planet Uranus. All right, then before I go on to more modern telescopes, I just want to very briefly talk about the electromagnetic spectrum. So because when we talk of telescopes, we always imagine optical telescopes. And then you see here that optical telescopes which we use actually cover a very small part of the electromagnetic spectrum. And I believe that a vast majority of you are physicists, so you know these things as well as better than I do. So here you go from 700 nanometers to about 400 nanometers. That is 7,000 angstrom to about 4,000 angstrom. And that is a band which is readily visible to us. But it is a small portion of the electromagnetic spectrum. And then at the largest wavelengths, you've got radio waves and then microwaves, infrared, optical, near infrared, ultraviolet, X-rays, gamma rays, and then very high energy gamma rays. So if you look at a star like the sun, it mostly emits in the optical. Because the sun is a, I'm sorry, the sun is a substantial star, which is very close to us. We can also see that it emits in radio and X-ray and so on, which was not known in the early days. But as the technology developed and we could detect electromagnetic waves of different kinds, we discovered that the sun emits all these waves. But that's only a small portion of the electromagnetic emission from the sun. But as you discover more and more violent objects, for example, if you go to quasars, so which are extremely compact objects, but they can be 10 to the 13, 10 to the 14 times powerful emitters than the sun. When you go to objects like that, which are called active, meaning that most of their energy is generated not through nuclear processes as in the stars, okay, but through different kinds of complex interactions between electrons and photons. So when you then in such objects, you find that there is some kind of an equipartition of energy emission. Okay, meaning that in every one of these bands, there is nearly equal energy which is emitted. So of course, as you go, the energy of an individual photon is very much lower when you go to radio waves, and then in the optical band, it's about 1 eV or less, and then you come to X-rays is much more, and then you can have 10 to the 20 EV gamma rays, meaning that the number of photons reaching us from any object is very much smaller. But nevertheless, the total energy is emitted in any band is equal to any other band. So which means that we have to understand the entire electromagnetic emission spectrum from an object to get a good idea, a holistic idea of the structure of that object. So here you can see the very familiar object called Crab Nebula, so which is just first observed by Chinese astronomers, as is very well known in 1054 AD. And this was actually a supernova explosion where a very massive star exploded into a supernova, and at the center of it remained a neutron star which is spinning very fast and which is a radio and X-ray and optical pulsar. So now what we are seeing now is the remnant of that explosion, which is known as a supernova remnant, and which is energized by the pulsar at the center. So you see that this is in visible light. You of course can't see it with the naked eye because it's very far away, but then you can see infrared, radio, X-ray, gamma ray, and so on. So you see quite different structures in the emission, because the higher the energy of the photons which are emitted, the more compact is the source of emission. And so the structure changes significantly. And in order to understand the Crab nebula or other objects like this, you need to do what is known as multi-wavelength astronomy. That is the mover and the shaker now. But there are further addition to that. So you've got something called multi-messenger astronomy now. So which is a combination of electromagnetic observations and gravitational wave observations. I mean, even though Einstein predicted in 1917 that gravitational waves must exist, it was almost exactly 100 years. Einstein predicted in 1916, and it was exactly 100 years later, in 2016, that the first direct detection of gravitational waves by the LIGO detectors was announced. Okay, so now we are multi-messenger astronomy. So even though we have the broad electromagnetic spectrum, and then and as I said, every region of the spectrum is important, but being able to observing it is a different story altogether. Because here you can see the across the spectral band the atmospheric opacity, because we have got the atmosphere with all sorts of gases in it, and it has different opacities and different wavelengths. And you see that it's pretty transparent in the optical, and there's a small amount of absorption which can be corrected pretty well. And in the radio waves, you can see that the here in this region, here are the higher energy regions, it's completely opaque. And then when you go to the radio region, it is completely transparent. And then for even longer wavelengths, it again becomes opaque. So what happens is that in order to observe, let us say, the X-ray spectrum or the infrared spectrum, you need necessarily to go to space. So the way people went to space was to fire these sounding rockets, and with the instrument on it which went up. Then the Tata Institute of Fundamental Research, for example, had a very substantial balloon Bose instrument program where you put a telescope on a balloon, a gondola carried by a balloon, and send it up. But for good observations, you require satellite platforms. So that is why you have got so many satellites going up, like the Chandra X-ray Observatory, sent up by NASA and European collaboration, the Hubble Space Telescope, and now the JWST. So these spaceborne observatories are completely critical for understanding the electromagnetic spectrum in those regions where the absorption of the atmosphere is almost complete. Right. So what are the tools of the astronomer, and what kind of observations do astronomers do? Now, the most direct is, of course, imaging. We always imagine the sky, the stars in the sky, and the crab nebula, and so forth. So here we are seeing an image of the sky. So the image has substantial information in it, because what happens is that you are seeing the extension of the object, you're looking at the shape of the object, and then what you could do is that you could also look at it through different filters. Meaning our naked eye, of course, takes in the whole electromagnetic spectrum, but you can put a red filter, blue filter, infrared filter, and so on, and then look at them, and then you can carry out detailed photon measurements on these images, meaning how much energy is being emitted by a star in a given part of the spectrum, which is optically visible, let's say. So that is known as photometry. So you've got the imaging, and then you've got the photometry. Then, of course, the most important tool is the spectroscopy. So you pass the light coming in from an object through a spectrograph, and then you've got very high resolution spectra, and then stars like the sun, they are not emission as such. The emission comes in as a black body because it's a very hot object, but as it passes through the atmosphere of the sun, some of the specific wavelengths and absorptions, you get absorption spectrum. Whereas the violent objects can have an emission spectrum. Then very important information is obtained through polarimetry. Okay, you measure the polarization of light coming from it. And what is of great interest now is time domain astronomy. Okay, where you are looking at the variability of an object. So if you're going to start, it by itself can vary because it is pulsating. Or you could have two stars going around each other, blocking each other's light, in which case you've got an eclipsing binary. And then there are, of course, objects like quasars, which vary because of very complex structural things in them. And then if we keep looking at one part of the sky, there could be suddenly an object going off there, meaning a supernova. So for example, there's about, there are so many supernovae going off in distant galaxies, and you can have programs where which you try to detect those. So time domain astronomy is now a great driver of the science. Then a quick look at the astronomical facilities which are available. I say for India. I'm not saying in India, because some of these are in India and some of these are abroad, but with which we have very significant partnerships. So there are telescopes all over the place. These are all medium-sized telescopes. They're doing good work. But two outstanding projects has been, one is the GMRT, which is the Giant Meter Wave Radio Telescope of the National Center for Radio Astrophysics, which is the center of TIFR. And this, of course, was designed and built by Professor Govind Swarup and his colleagues. And it has got 30 dishes, each 45 meters in diameter, and which is spread out over a region of about 30 kilometers across. So this observes at relatively lower frequencies. It's the best and the greatest instrument at lower frequencies. About 50% of it is used by India and 50% by people from abroad through proposals. And absolutely great discoveries have been made by it. And another very successful instrument is AstroSat. Okay, so which was launched in 2015. And AstroSat observes at optical, optical, UV, and X-ray wavelengths. X-rays, of course, are the most important for this one. And then, so it has got the telescopes all point in the same direction, as you can see from the diagram here, except for one instrument which is down there. So therefore, you are able to observe any possible objects at these wavelengths very simultaneously, which is an extremely important advance, because some of these objects vary very fast. They vary in fractions of a second. And because different emissions are coming from different regions of the object, the variation in different emissions, there's a time lag between them. And by observing the time lag, you are able to give the space distribution of variation of emission at a particular wavelength. So AstroSat has again been phenomenally successful. It was designed to be active for a few years, but it's still going on strong. And the main reason is that ISRO was so successfully in putting it in the correct orbit around the Earth. It's in a relatively low Earth orbit around the Earth, and getting everything going exactly right, that a lot of fuel was saved. And therefore that fuel can be now used to turn the satellite to the direction that you want and so forth. And of course, the very high quality of the instrumentation, which has kept them going for such a long time. Then later this year, there will be a solar observatory called Aditya L1, which is being launched by ISRO. And the telescopes on this, just like the instruments on AstroSat, similarly the instruments on Aditya are all being built by different institutes. And one is being built in IUCAA. And so it will be a great solar observatory. Then there are three large projects. You've got the 30-meter telescope, which will be one of the biggest optical telescope when it is built and ready. And then you've got the LIGO India detector, which is to supplement the two detectors which are there in the US and the square kilometer array. So on the top two projects, India, the LIGO India project will be entirely built in India. The main instrument is provided through the USA. The TMT will be located in Hawaii, but there are a lot of political problems with that decision, which has, with the possibility of locating it there, which have delayed matters very much. And India is a 10% partner in the TMT. So this is not a money order partner, in the sense that we don't just send money and get 10% of the time. We are building very important components of this telescope. And similarly, we are making very important contributions to the SKA. Now, as some of you would know, Pune is a rather compact city, and things happen geographically, everything is geographically close to everything else. So from this point at which I'm sitting now in my house, within 5 kilometers on each side, there are maybe 15, 20 very large national institutes and laboratories. So similarly, so when you go to IUCAA and NCRA are on two sides of the road. So, and in one, the control system for the TMT is being designed, and in the other, the control system for the SK is being designed. Okay, so this is a good example of what happens in Pune. So now, modern telescopes. So, and I already shown you examples of it. The main thing is that unlike the earliest telescopes we used, these are reflecting telescopes. Okay, meaning that you've got a mirror rather than a lens. That is because a lens produces all kinds of aberrations. It absorbs the light. They're very heavy and they're necessarily a long focal length. So which makes a telescope very difficult to control. So here you shape the mirror. The mirror itself, these are metallic glass mirrors, but these are not, they itself are not reflecting. Glass is not reflecting. When you coat it with a reflecting surface, then light comes in from a distance and comes to a focus here. So you need to put something here. And in the old days, you put an instrument. But now you put another mirror, which lets you take the light either back through a hole in the mirror or on the sideways. And depending upon what you do, it's given a different name. So here, for example, you see a Cassegrain telescope where here's a mirror, there's a hole in the mirror. So light comes in from a distance, it hits the primary mirror, the size of which determines the collecting area. Then it goes to a secondary mirror and is reflected back through a hole. So you may see that, you may feel that all these things obstruct the path of light, but you know that you can just work out the areas and you find maybe 10% of the path is gone, 20% of the light is gone, but that is all right. And then you need a mechanism for keeping the telescope pointed in the same direction over a period of time. So because when we observe with our eye, we have got an integration time of about 1/10 of a second. And the lens has got a diameter of a few millimeters. So, but here, what you want to do is to have very long exposures. So as the Earth rotates, you need a mechanism to keep the telescope pointed in the same direction. And that needs to be done very accurately. And which is not very easy because of the weight of the telescope and so forth. So here is a example of this. It belongs to the Indian Institute of Astrophysics. It is located in Hanle in Ladakh, quite far from the capital. And then you need to go there because it's very dry. You get a substantial number of clear nights. And because of the dry atmosphere, you can observe at near infrared wavelengths, which are very important to astronomy. And here, so when I was in school and I first started reading about astronomy, I quickly read that there was a telescope called the Palomar 5-meter telescope, and which was the biggest telescope in the world. So just like the 4-meter telescope of Herschel, 40-foot telescope of Herschel. So this was also the biggest telescope in the world for a long time. And it made extremely important discoveries, some of which were actually made when we first joined TIFR. I remember one of the first papers I read was called on the ability of the 200-inch telescope to distinguish between cosmological world models. So study cosmology with it by Sandage. So that was about a 40-page paper. And I asked library to Xerox it for me. At that time, we had manual Xerox machines, were barely there. And then 120 pages of Xerox. And those people nearly had a fit. They said, nobody Xeroxes 120 pages. So it was a completely different time. So then, now you see here the 200-inch mirror, 5.1 meters, and it is about half a meter thick at the center, and it is 60 centimeters thick at the outer edges. So it has got very substantial weight, and then you really can't, and it's extremely difficult to maneuver. So I not only read that it was the biggest telescope in the world, but I also read that you can never build a bigger telescope. Now, a strong statement like that, of course, immediately gets refuted. And that is what science is all about. And people did build bigger telescopes, substantially bigger telescopes. And the first one was a Russian telescope over 6 meters in diameter, but it never has really worked terribly well. So what we did, why can't we build bigger telescopes according to that theorem? And that's because the weight of the mirror becomes so much that it'll just crack under its own weight. right? So now, what is the advantage in building bigger and bigger telescope like this? So here you see the picture of a galaxy on the left, and you don't see much detail here, but it is taken by a 2-meter telescope of something which is known as the Sloan survey, which surveys objects all over the sky, which is visible to the telescope. This has been one of the most successful projects, because using data which has come from this, which is completely in the public domain, I mean, thousands and thousands of research papers have been written. So you see that the blue part shows you if you take a cut across the galaxy, you get the intensity distribution, which decreases from the center to the periphery, and you can see how far you can go with a Sloan telescope. And then the same galaxy was observed by the Palomar 5-meter telescope, and you see with a 1.6-hour exposure. That's a really long exposure of a single image. And the data was provided to us by Ashish Mahabar and a student of mine from Raipur. He was actually a student of Ravi Shankar University. He had extreme skill in taking an image as faint as you can go. I mean, because the image is there, but analyzing it to extremely faint levels, he was a great champion at. And you see here, at this point, you are reaching 5% of the background light in the sky. So the sky has got a background light which cannot be minimized, because it is simply the light due to, it is a total integrated light output of the billions of galaxies which are there in the universe. No one can remove the galaxies. Okay, whereas Lakshmikant's analysis took him to 0.1% of the sky. Okay, but in order to go so deep, he needed the image from a big telescope. So how do we build bigger telescopes? So in this very beautiful picture, you see 4 telescopes which have got names in the South American Indian language in Chile, and then there are 4 telescopes, each of which is slightly more than 8 meters in diameter. They're all in a straight line, and you've got 4 telescopes because, of course, you can do 4 times the research with it. But the idea is also to combine the light and to have an interferometer. And this has been a remarkably successful telescope. So how did they build such a big telescope with 8-meter diameter? That is because they used, sorry, I have to move this around so I can read the picture. So they, you can see how big is the mirror while it was being polished. And then you can see the 8.2-meter diameters, and you can build it because it's a thin meter. If you remember, the Palomar mirror was 0.5 meter thick at the center. This is only 17.5 centimeters thick. It weighs only 23 tons, even though it has got an area which is 8 by 5, 1.6 squared, 2.56, 2.5 times the area of the Palomar telescope. Okay, so it weighs only, and it's built from a glass ceramic zero door. So which means that you take a leap into technology and you build new material, a thin mirror which weighs much less, and then you can build telescopes. But at this point, you really have reached the limit for various reasons. But the most important thing is that, the important here, these kind of mirror blanks are extremely expensive and hard to find. You polish it, and if you damage it in any one position, you have lost the complete mirror. It is very difficult to build the support system for it. Okay, and then to maintain the mirror. And then another problem is in transporting the mirror. So wherever you make that mirror and polish it, how do you transport it? Because you don't have to transport it, let's say, from one part of Bombay to another part, or from Chandigarh to Mohali. I mean, you'd have to transport it sometimes over hundreds and thousands of kilometers to extremely remote locations. And look at this, climbing up the mountain in Chile. And that is an extraordinarily difficult challenge. So therefore, how do we make progress? Okay, how do you build a 30-meter telescope? By segmenting the mirror. Okay, meaning that break up the mirror into small parts. And then you have got 2 such telescopes. You have got the Keck telescopes. Okay, these are twin, again for the same reason that there were 4 of the VLT. And then So you see that these two telescopes here, and each of which they are identical telescopes, and you can use them as interferometer. And so what is the speciality of the mirror? Is that the mirror is segmented. Now just see here how big is the mirror. And you can see that this red thing here is a person with outstretched arms sitting there. It shows you how big is the mirror. And this is just a 10-meter mirror. And the 30-meter mirror, or there is a an even bigger mirror about the European telescope, and it is substantially bigger than that. So what you do is that the mirror is constructed from segments. So these are small segments that which are there. A small meaning that each one of them can have diameter more than about 1.5 meters or so, and which makes it a good, respectable telescope in its own right. The mirrors together, they form the reflecting surface. Now, you can't have this segment and stick them together. They will not retain the rigid form as you rotate the telescope. What you need to do is to have active optics. Okay, meaning that behind each segment, there's an extremely complex mechanism. And that mechanism senses the overall shape of the mirror and corrects each mirror at least once per second. Okay, and then you maintain the shape of the mirror. And this technology is called active optics. And the active optic components for the 30-meter telescopes are being built here in India. Right, so you see that the 13 hexagonal segment, each 1.8 mirror. Until recently, the biggest telescope in India was just more than 2 meters. Right, so, and then you use something called adaptive optic systems to get image. So I'm telling you here what is adaptive optics, which is another great innovation. And that is that when you look at a star, it appears to be twinkling. And that is because the star is essentially a point object. The ray of light enters from the star to your eye. But because of the varying refractive index of the atmosphere, many times a second, the light ray keeps jumping around. As a result of which, if you look at it, the eye, you see twinkling. And if you look at it with an imaging detector, you see the light scattered around. And very roughly, the spread of light has got a Gaussian distribution, which a full width of half maximum of about 1.5 arc seconds. So if you are the best site in the world, you get about 0.5 arc seconds. So if there are two stars which are closer than that, you will not be able to resolve them. And what we would like to do is to remove this effect. And the way to do that is, you take, you can see here that there are simulations, and you can see a convolved image because of the effect of the atmosphere, the deconvolved image, and what sharpness can be achieved by that. And the way you achieve it is, you shoot a laser beam up into the atmosphere and create a star with it, a point source. Look at the shape of the point source and compare it with the original shape, which you know about. That is because you have designed the laser beam yourself. You know the shape. And then you have got a flexible mirror, which varies about one shape about once in a millisecond, okay, to counteract the effect of the atmosphere. And then you can restore the image. This is known as adaptive optics. How much more time do I have? About 15 minutes, I think.
Yes, please take your time.
Okay. I'll not keep you for too long. So you see, what we have done now is that first we looked at the Galileo's telescope and saw what amazingly great observations he made. And now we have come to a modern telescope. And at each one of these steps, at every one of these steps, there were new discoveries which were made. Okay, so let us see what was found by telescope. The Keck telescopes and the VLT. So here are two people, Reinhard Genzel, located in Munich, who used the VLT, which belongs to the European Southern Observatory, and Andrea Ghez at University of California in Los Angeles, and she used the Keck telescopes. And these are completely independent groups, worked on a simple problem of trying to see what is at the center of a galaxy. And their work, which is the results of which are amazingly simple. Okay, and so and that work won a Nobel Prize in 2020. So they shared half of the Nobel Prize, and the other half of it went to Roger Penrose for his theoretical work on black holes. Quite a lot of it was done with Stephen Hawking, who's no more. So, so you see, this is a picture of the Milky Way. And when I was in school, I used to live in Hubli, and there from the doorstep of our house, every day I could see the Milky Way as a Milky Band in the sky. Now it is almost impossible to see it from any city. But if you go to darker space, you can actually see the Milky Way. And what you see here of our own galaxy is the center of our galaxy. And it is in the constellation of Sagittarius. So from many points in India, you can see the constellation of Sagittarius close to the horizon. And then you can see the center of the Milky Way. Right? So what is the shape of the Milky Way? So you can see it here. This is not a simulated image, it's an actual image of the Milky Way. So how do we take it? Because we are inside the Milky Way. When you look at the band in the sky, what you are seeing is stars which are very far away. Because the 4,000 stars which we see with the naked eye are spread out around us, around the sun. And then there are many more stars like that. But as the stars go further and further, they just make a band in the sky. So you take a near infrared camera and point to different parts of the band, and you take a picture of it. And then you just put the pictures together. So why near infrared? So that is because you see here in this image of the Milky Way galaxy, you see this brown thing there, which is just dust in the galaxy. The dust comes from earlier generation of stars, which evolved, created heavy elements, and exploded. And those heavy elements form the dust which is there, which actually absorbs light. So the shape of a Milky Way is that there's a disk and then there's a bulge. And you look at it from the top, you see the spiral arms in the disk. Okay, that's the thing which all of us are familiar with. And the size of it is 100,000 light years in diameter. And so what we would like to do is to see what object is at the center of the galaxy. So where do we go? We can't see the center directly. And that is because we are 24,000 light years from the center. So stars there are substantially fainter and are covered with dust, which actually makes them even fainter. But radio astronomers are not limited by this. And they soon found that there is a very compact object called Sagittarius A in the constellation Sagittarius, which is not moving around. And so which should be massive. Because less mass, it always moves around. And then that is considered to be the center of the galaxy. Right? So then people discovered Sagittarius A star. Okay, so why A star? That is following physicists. They said because it's an exciting source. Okay, so they called it A star, which is the real center. So now you see, using all the modern technology which I already explained to you, use big telescopes, then use near infrared camera detectors, because that's where the obscuration is the least, and use adaptive optics, because this is the center of the galaxy is an extremely crowded field, and you want to separate out the stars there. You want to have as high resolution as is possible, and therefore you use adaptive optics. Doing that, look at the scale of this. So our galaxy, the size is 100,000 light years. The size of this box, if you look at this bar here, is about 4 light months. Right, so you are really gone to the center of the galaxy and seeing stars there. And here you are zoomed in, and here is Sagittarius A star, which we think is the center. Okay, and then look at these stars here. So, so this star, the star which seems to be engulfing Sagittarius A star, it's actually just the limitation of the equation. That is the closest, and it's called S1. So the idea is that S1 will be going around A star if it is the center. So it will come from somewhere, it will go move close to it and go away. And you see that I think that the orbital period of the sun around the center of the galaxy is like 200 million years. Okay, but the orbital period of this star turns out to be about 19 years. Okay, so you see how close to the galaxy we are. And what these two groups did was that they mapped over first the results came from 1992 to 2002. Okay, a 10-year period. And then they published the results. And then now they are gone on to 2010. So what do we see here? What is the shape of the orbit? Okay, you see that it is it's absolutely perfectly an ellipse. And what is very interesting is that working in the 17th century, Kepler had done exactly this. Because his supervisor, Tycho Brahe, gave him the data on Mars. And then Kepler charted its orbit in the sky. And he got this shape. He suspected that the shape was an ellipse, but he did not know what was the equation of the ellipse. So it took him 20 years to find that out. But then he gave 3 Kepler's laws, with which all of you are so familiar. And said that orbit is elliptical, and then the sun is sitting at one focus. And what are you seeing here is that the orbit is perfectly elliptical, and Sagittarius A star is sitting at one focus. And so, and the blue dots are by one group, and the red dots by other group. Because the details of the determination of this orbit are incredibly complex, and you need 2 different, totally independent groups substantiating each other's results. And so they got a period, sorry, not 19 years, 16 years. And then it is highly eccentric orbit. And you can, unlike Kepler, who could not measure the mass of the sun because Newton was still into the future. So now we know how to do that. It is 4.2 million times the mass of the sun. So we know now that there are supermassive black holes at the centers of many galaxies. And here what we have established is that there's an extremely compact object which is dark and which is at the center of our own galaxy. Now there are every argument that you could think of points to it being a black hole, but there is no direct confirmation of that. But to add to the beauty of the result, just look at this. So you'll see here, right on top of the image, that the ellipse is not closing on itself. Okay, so the idea there is that why is the ellipse not closing on itself? Because there's a small motion of Sagittarius A star. Okay, so which sort of kicks the ellipse a little bit and therefore doesn't close on itself. And you may imagine, is the accuracy good enough? It is good enough because error bars are much smaller than the sizes of the objects. But then it becomes even more interesting. Right? So what they did was that over the last couple of years, they invented a new instrument. It was not invented in the last couple of years. It was got ready in 2020. It's called gravity. Okay, it takes light from the 4 telescopes of the VLT, combines them together to get a measurement accuracy of 65 micro arc seconds. And then you are really talking of very accurate measurements here. Right? And then what do you see? So you see here actually that the ellipse precesses. Okay, meaning that in one orbit, if it is like this, in the next orbit, it will be like that. So the perihelion of the ellipse moves slowly. Okay, and of course, it'll take a very long time to go around once fully, because 16 years is the period of one orbit. And what is the precession due to? It is due to general relativity. So all of you would have heard that there is a precession of the perihelion of Mercury, 43 arc seconds per century. This is very much greater precision. That is because the object, the black hole, is much more massive, and it is moving extremely close to the black hole. So this is very pleasing. Okay, meaning that you have built instruments, you have observed for 20 years, and then you have established that there's a supermassive black hole that has got so much mass, and you are seeing this wonderful general relativistic effect. But this is a weak general relativistic effect, which Einstein first established was present. Okay, so as we go into the observations, you'll see strong effects to do with the event horizon of the black hole, which would mean that you established that the black hole exists. There's a picture of the 30-meter telescope. Okay, now optical UV and near infrared astronomy from space. So I want to accelerate. You see here, why do we need to go to space? Because atmospheric absorption, atmospheric blurring, and the need for continuous observation. There's no day and night when you go there. And so here you see, one moment, let me move this out. A picture of the Hubble Space Telescope, launched in 1990. It is still working. And there's a big screw up because people could confuse between the metric system and the British system of making measurements. The Americans still use feet and inches and so on. But that was taken care of by actually going there in the space shuttle, okay, and repairing the telescope. And now it has been extremely successful. And you see that it has produced more than 19,000 reference papers. Okay, I mean, that is the kind of success that in any experiment I should have, right? So you see, for example, at the beginning of the 20th century, there were only 3 white dwarfs. And here in a globular cluster, and a simple single image, every white circle here has got a white dwarf in it, which shows you how substantially the thing appears. So here is a picture, a very deep image taken in 2000, released in 2012. As you notice, the Hubble extreme deep field. The deep field was in 2002, extreme deep field. And here, so this is a 2 billion second exposure, right? And then what you see here, you can see galaxies clearly. You see almost no stars because a tiny field high up from the galactic equator, and every little dot here is actually a galaxy in its own right. Doesn't matter how small the dot is. And so what is the implication? A galaxy has 10 to the 11 stars. So we know that there is probably a planet around every galaxy, at least one planet. So if this dot has 10 to the 12 planets, okay, which means that maybe a million civilizations. So even if you're very pessimistic. So that is the kind of scale that the universe has. Right, so this is a more shallow field that a student of mine had worked on. So as you zoom in, you can see each dot developing into a galaxy. Okay, so now the last part of my talk, the James Webb Space Telescope. So this one, actually the story of this talk is that the director of NCL National Chemical Laboratory here in Pune, so he and I were going to TCS a few months ago in a car. And he asked me about the James Webb Telescope, about which I knew nothing, which is true even now. And I just told him something, and he said, come and give a talk. So I gave a talk, and I don't know how Arun heard about it, and he asked me to talk about the same subject here. So the James Webb Telescope, the Hubble Telescope has got a mirror 2 meters inside. This is about 8 meters. Okay, and then the whole thing is in space. And how do you send 8 meters of mirror to space? So what they do is that it is completely folded. So here are some details. One moment. And launched is Christmas Day of 2021. Weight of the mirror is 6 tons. Primary mirror 6.5, not 6.5, 16 segments. It works exclusively at near infrared and medium infrared wavelengths. That's 0.6 micron to 28 microns. And it is at a distance of 1.5 billion kilometers. Unlike the Hubble Space Telescope, which is going around the Earth. Okay, so I'll tell you why. And you see, to put this in orbit, what they did was that when it was launched from the Earth, it looked like this. Everything was folded up. And it were in extremely complex maneuvers. It was unfolded, the mirror came out, and the mirror was fully unfolded. And all the instruments had to come out. And then you need the solar antennae in place, which are very large. The solar antennae is like a football field. Okay, and then this whole thing took 9.1 days. And obviously nobody slept for the 9 days. Now the people, because it started off with a $1 billion project, then it became an $8 billion project. It took many more years to complete than anticipated. It's a NASA and European effort, but it is finally in space and doing wonderfully. So now where is this telescope located? So if you look at the Earth, the Sun and Earth system, these are 2 point objects, one of which is much less massive than the other. And when these objects are going around each other, you get 5 special points, which are known as the Lagrangian points. Okay, so the best way to understand a Lagrangian point is to say that there's some kind of a local minimum or a cusp there. Right, so the Lagrangian point between Sun and the Earth is called L1, and here the other point is called L2, which is at a distance of 1.5 million kilometers from the Earth. So this spacecraft was sent out, and now it is sitting at L2. So the point is that if you keep it at L2, it will remain at L2. But that becomes unstable. So what they do is that they send it on a small orbit around there. And what is it orbiting? There's no mass there. And that is because the fact that there are these two objects, the Sun and the Earth, and the fact that they are going around each other gives rise to this. And what is the advantage of going to L2? Is that you can point away from the Sun, and you can just keep pointing away from the Sun. So half of the telescope, half of the craft is towards the Sun, half of the craft is away from the Sun. And it will always and forever remain like that. And then, so you see what happens here is that here you have got the mirror, and because this is working at near infrared, you need cryogenic temperatures here, which is not so difficult because after all, it's terribly cold in space. The difficulty comes from the other side, because that is exposed to the Sun, and the temperature is very large. I mean, I've forgotten how much it is, but it's very large. And you need obviously extremely good insulation between the two, and you need cooling systems. And then you, so one part is hot, the other part is cold. And it's all working. I mean, this is not somebody's imagination. Look at this here. So they give it in Fahrenheit. What do you do? Okay, so this is minus 233 Celsius, and this is 85 Celsius. And so you need to control the temperature like that. Right, so you can see here the package of instrument which is there. These are all near infrared images and spectrographs. Okay, so NIR ISS would be near infrared imaging I forgot. And so you've got these wavelengths there, right? So so then now they started releasing early images in July, and then we started. Everybody was quite taken aback at the kind of resolved images they could find. So they look like a creature here, one of the science fantasy films, but it's actually dust lanes. I keep talking about dust. You look at the details, and then there are all these things here are stars which are forming, and then they illuminate the dust. And dust is absolutely essential for the formation of stars. Without dust, there will be no stars, or difficult to form stars. And then you see, if you compare this with the older image, so this is near infrared, this is mid infrared, and near infrared, and then you see this is the one taken with the Hubble Space Telescope. So you see the amount of detail which has now become available. The problem with such detail, of course, is that you cannot now do back of the envelope calculations. You cannot even do simple analytic calculations. What you require is extremely heavy computing approaches, right? Because this all becomes it becomes hydrodynamical things. Then you have to put in dust, you have to put in magnetic fields, and in some cases you have to add GR to it. Okay, so you may say that general relativistic magnetohydrodynamics. So I used to call those Harakiri projects, okay, meaning that if you do a PhD in that, you're not going to get a job in astronomy. But those times have changed now. The last two faculty members that we have got in IUCAA do this GR and MHD, okay, because that has become so important and inescapable now. They can, of course, immediately get a job in any finance company in the world. Okay. Right, so this is another very beautiful picture which is taken of a pair of galaxies which are interacting, because interaction between galaxies is extremely important for determining the structure. And here you can see the HST image, and to the right you can see the normal image taken from Earth. So you see the progress which is being made. Then this particular object, this object here, is the furthest galaxy known to us. And it has got a redshift of 12.1, and it is a look back time of 13.6 billion years. So which means that the light left this galaxy only about 350 billion years since the universe came into existence. So what is so surprising is that at that great distance, at that early time, so you have got this kind of a developed galaxy. Okay, so which created a lot of problems on the theoretical side. Right, but I want to end my talk now in 2 minutes, showing you some detail which is observable. Meaning these are all images. Astronomers work on images, but something substantial which physicists will like. Okay, a spectrum and a deduction from the spectrum. So the picture that you see is not a real picture, but it represents an exoplanet. So exoplanets are planets outside the solar system. The first one was discovered in 1995, and now there are thousands and thousands of them known. So this is an exoplanet called WASP 39P. So, and this one, I have to remove these things here, is a gas giant planet, meaning that Jupiter is a gas giant. They have got a mass about 30% of the mass of Jupiter. It moves very close to the star. This is a remarkable thing about exoplanets. Because we discover very large exoplanets moving very close to the star because that is easy to see. Period only for 4 days. And the temperature is about 630 K. Now, the thing is that, how do you discover these exoplanets? One of them is eclipses. Meaning that as an exoplanet moves across its star, the light from the star dims. Okay, and then you see, if it happens in a particular way, you see an object obscuring it. It's exactly like the eclipse of the sun by the moon. The difference is that neither the sun nor the moon here are resolved. They're completely unresolved objects. You see only one object there. You just see its intensity decreasing. And then here is a planet, and surrounding the planet is the atmosphere. And what we are interested is in getting a spectrum of that atmosphere. So you see there's an unresolved object. So first of all, there'll be a lot of perturbations of the spectrum by our own atmosphere. Then you are seeing the very bright spectrum from the star, which has to be subtracted out to get the residual transmission spectrum from the planet. So what do you mean by transmission spectrum? Meaning that the light goes through the atmosphere of the planet. And in that process, there is absorption. And look at this remarkably beautiful spectrum which has been obtained here. Just a few months ago, the papers have been published. It is possible that many of the results will change because the calibrations are still in progress. And you see, what do you see? You see water. Right? So where is water, there is life. Okay, then you've got carbon monoxide, you've got sulfur dioxide. So does it mean that this is the first ever spectrum of an exoplanet atmosphere? It is not. You could do that from other satellites also. In fact, India is also planning to send up a satellite for that purpose. But the resolution was much poorer. The mirrors were much smaller. So therefore, for example, sulfur dioxide is being seen for the first time here. So it is a little bit difficult for me to get excited about sulfur dioxide. Sulfur dioxide has. So the problem is that the people get excited because of the implications. So what are the implications? You see, SO2 has been detected for the first time. Sorry. The SO2 has been detected for the first time in the exoplanetary atmosphere. And then in order to form this kind of an atmosphere, you need to form planetesimals, accretion of small little planets like meteors, slightly bigger ones to form it. Then there's a lot of oxygen, which indicates that the exoplanet initially formed far away from the central star. If you're closer, then the radiation from the star will not got rid of the oxygen pipe. So you see that, first of all, you make these measurements, and from those measurements, you get all these nice implications about how so many different kinds of what you call solar systems are in existence. They're totally different from ours. And why are we not finding systems like ourselves, our own system? That is because our own system has got only small planets close to the sun, and such systems are difficult to detect. Right? So we are detecting what we can detect. And only by making better and better probes, you see it. But even now, we have found many Earth-like planets. And Earth-like planets in the habitable zone, meaning that Earth-like planets, rocky planets, which are so close to the star that water vapor can exist on them. Means temperature is neither more nor less. So these are very substantial progress. So I will stop my talk here. I'm really sorry to have exceeded my limit. But the problem is that because you're all physicists, I feel like putting in a little bit more detail. And here is something which astronomers would like to do. Thank you.
Thank you very much, sir. Very informative and very stimulating.
Absolutely brilliant. Great talk.
Thank you.
I think people will hear and listen to it again and again in the offline mode because you give so much of an information. I think one has to listen to it repeatedly to get it in parts. Thank you very much.
I'll tell you another problem with this offline mode. See, normally you stood at the dais and you gave a talk, and one or two people in the audience discovered that you didn't know too much about what you were saying. Okay, but that was the end of the matter. But now, I mean, again and again, people, there is some chance that some expert will see it and they say, "Ye kya bakwas kar raha hai?" Okay, so I keep getting worried about that aspect.
I'm not worried, because you have to make people ask questions. So even if the sentiment that you have expressed is correct, it will lead to more explorations.
Yes.
Okay, so now that we have all these IISERs in the country and there are these young people coming in, if in their spare time they keep listening to these things, because all these talks will not get done in their respective institutions because their faculties are very small in number vis-a-vis the kind of institutions that you and I did PhD. There the students were small, number of talks were more, and lots of things we got exposed to. But that cannot happen in the smaller institutes today. The only way of giving exposure to this thing is to have these talks recorded and then put it in the offline mode and disseminate information that such and such things are available. And these people are available within India. So if people want to ask questions, they can reach up to them. An Indian student would find it hard to reach up to a Harvard professor, but they can always reach up to their Indian scientists within India and they have a chance of meeting them and so on and so forth. So that is why talks like yours that we organize, I personally believe, are a very important resource.
There are also other problems. Now, if you remember, 50 years ago, when we attended colloquia in TIFR, the hall used to always be full.
Yes.
Okay, and Virendra Singh used to be sitting in the first row, and you always turn back and see who is there and who is not there. Yes. Okay, but I mean, the hall used to be full, regardless of whether the colloquium was on molecular biology or astronomy or physics. Right now, students don't come to talks.
Yes.
Okay, but that doesn't mean that they don't listen to talks. They like to listen to talks in their own time and in their own way. Okay, so they put on the laptop, put on music, they're eating something, drinking something, and then listening. So that's also another reason why these recorded talks help. Because many times people I don't know at all come and tell me, "We heard your talks on YouTube."
And that is how I accessed your talk, okay, at NCL.
Essentially, it has to be a mixture of both.
Absolutely, absolutely.
I mean, we could not have heard you, but for the ITS, the online facility available now.
Yeah, you see how much better it would have been for me to be in Chandigarh or Mohali, listen to.
But you are welcome to visit Chandigarh.
You are welcome.
And then the best thing to do would be the lunch which followed.
So that
Anyway,
is the extension of the
wants to
lecture.
host such talks in Tagore Theatre, which has 1,000 capacity. DharamVir had hosted Padmanabhan's talk, and it was attended by more than 1,000 people from the Civic Society, more than half the school students from class 11.
Professor.Sathyamurthy is witness. He himself was one of the speakers at one of the occasions.
Yeah.
And Tagore Theatre we can arrange such talks at Tagore Theatre again, because now that everything is open, we'd love to have you in physical mode, because this lecture is very, very exciting.
So I'll definitely come. I'll love to be in that area. Definitely come. Thank you very much.
And now I request the audience to raise hands, whoever wants to ask a question or to comment. This morning, 2 students phoned us. Where are you? Nanak, Aditi, I'm going to ask you to unmute. Where are your bachas? Please raise hands.
Aditi is there.
Yeah, hi ma'am. Hello sir. How are you?
Hello.
Aditi, we are fine. Where is this kid who was wanting so much to join this morning? Usko bulaiye.
Akshraj.
Akshaj.
Ma'am, I believe he left the meeting after like all. So I'll just ask him to join it again and he'll ask the question.
Okay, thank you. So anybody else? Anuj, can you see any activity on Facebook?
No, ma'am. But the participants on Zoom can also write their message in the chat box. If you don't want to ask, you can write it in chat box, please.
So I see
And the
KP
mic
Singh
is
in the
off.
audience. KP, would you like to say something? Kulinder Pal?
Professor Kant is raising hand.
Yes,
Professor Kant, please go ahead.
It's a pleasure to listen to these astronomical talks. It has shown me the astronomical levels which the engineering has gone to, the support which the manufacturing engineering has provided to this astronomy is really mind-boggling, I would say. The manufacturing required for that, you see, big telescopes apparently doesn't fall into the normal manufacturing which I have been teaching for so many years. It's really interesting to know the amount of engineering required in this astronomy. Thank you, sir. Thank you a lot.
Thank you very much.
Thank you for your comments, Professor Kant. And now we have something.
Madam, good morning. This is Professor Vijay Kumar from Bangalore University.
Yes, good
Can you
morning,
hear me?
Professor Vijay Kumar.
Yeah, it was very informative, and Professor Kembhavi sir, whom I have met several times at IUCAA personally. I liked the talk very much. It was quite informative. And sir has gone through the history of the 400 years astronomy, right from 1612 or whatever. So I thank you very much, sir. And I wish to have the a copy of these slides of the talk by Professor Kembhavi sometimes, because I also want to make use of some of the slides with the permission of the Professor Kembhavi. Is it possible to have the copy of the talk?
Sure, I can send it to you.
Yes.
It would be available on the SPSTI site. Okay, and with everyone, we'll share the link from which you can access it. At any time, you can go to the SPSTI webpage, and all the talks are listed there that we have held during the pandemic period. But we'll make a proper index and put it there, author-wise, as well as group them in different subject-wise. That responsibility, I think the SPSTI.
We are already doing it. Within a week, it will be there on the site, on the website.
Okay, madam. Thank you, madam. Because we are offering astronomy elective in our Bangalore University. Students are also very curious and want to make use of some of the slides again.
Wonderful. If there are topics you want to be covered, please let us know.
Yeah, surely, madam. Surely, madam.
Thank you.
Thank you.
Now, Professor Dua has been wanting to say something. Professor Dua, please unmute yourself.
Good afternoon, Professor Ajit. What a fine expository lecture. I'm, of course, a biologist, and to pick up few things for a biologist were really rather tough. But I have two small queries. One is a very simple, of course, that is that how Galileo was affected by the work of Copernicus, whose student Lochen wrote the book on the revolutionary bus orbium. At the start, was he through with that book or inspired by that book and that the heliocentric model of Galileo, Copernicus? And
yes, no, it was not Galileo. I mean, Galileo knew of Copernicus' work. It was just that there were two models, geocentric and heliocentric. And Copernicus' model, I mean, I did not know until relatively recently. It was a combination of both, actually. Because you see, very interestingly, Copernicus thought that the planets move in circles around the sun. Okay, so that introduces some errors between your predictions, because after all, your model has to predict where Mars will be at one time, and there are errors coming in at that time, and therefore you have to introduce these epicycles, which those Greeks used to have a couple of millennia ago. Right, and all astronomers from all countries, including India, had to have these epicycles. Okay, so it was Kepler for the first time who said that the orbit is an ellipse. Then it became a purely heliocentric one. But Galileo's contribution was to prove this, because he said that the phases of the Venus would not appear in the form that they do if it is a geocentric thing.
No, Galileo Copernicus just wrote in a book the Revolutionary Bus Omni Erbium.
Yes, yes.
And Lochen introduced that book in after his death in 1543. And
yes,
Copernicus came just Galileo came 20 years later.
Later, yeah. But I'm not aware of this other contribution that you're talking about. So I'll go ahead and look for it.
Now, second question concerned with your second part. You see, the next 30, 40 years at the global level, Indian level, level belongs to the global warming. And after all, the global warming is a byproduct of the accumulation of certain chemicals in the space also, which were responsible for you see the UV spread this sort of a cancer in Australia also, and that has been sealed, of course, with few thick. Can this sort of astronomy can be applied to predict the global warming for the next 30, 40 years? Every year we talk about global warming, but can these instruments be used for the composition as a predictable model, say for the next 100 years?
You see, answer is a little bit indirect. Okay, meaning that you can't apply your astronomical knowledge to it, but on the other hand, the techniques can be applied. Okay, so when we study all these atmosphere, our own atmosphere, the other atmospheres, other planets, you see these chemicals, which giving you basically an idea on what are the different variations which are possible.
Now,
so,
sorry for interrupting, but if sulfur dioxide composition, this is the biggest culprit so far as a global warming.
Yes, yes.
And if it's particles stay in the colloidal form, is increase further and can be predicted. Something can be done like that of the skin cancer in what was done in Australia, and the black hole was sealed at that time. Black zone was sealed.
Because certainly the knowledge definitely flows from one side to the other.
Anyway, so at this time, of course, you see that I don't see any light at the end of that tunnel so far as the prediction about global warming is concerned.
Yeah, there is Rudra Swami wants
to say. Yes, Rudra Swami and then Aditi.
Yeah. Good afternoon, sir and madam. So I'm a retired professor of Bangalore University. So I was, I was fortunate to attend this refresher course held in IUCAA in the year 2020. And Professor Kembhavi, I was fortunate to listen to Professor Kembhavi's lecture. And in addition to that, he was conducting parallel sessions on photometry. So for 1 month, so much I interacted with Professor Kembhavi. So now I got an opportunity again to listen his lecture now. So it was very exciting. So thanks a lot to Professor Kembhavi and all the organizers. Thank you, sir. Thank you very much.
Thank you very much for your compliment. Thank you.
Thank you, sir.
Thank you. Thank you very much, sir.
So, Kia, there is someone.
Thank you. Aditi, please unmute yourself. Or Akshaj, Akshaj,
yeah.
please unmute.
Akshaj is there and he
Hello.
would like to ask some question. Yeah. Yeah, ask Akshaj.
I would like to ask, what are your thoughts on the hunt for dark matter?
You would like to ask what is the meaning of dark matter?
No, what is your idea on how to find dark matter?
Yes. So do you know what is dark matter?
Yes, it is currently the matter that constitutes 70% of our galaxy, and it seems to have gravitational properties, but we have not been able to study it as we have not been able to find it yet.
Yes. So there has been a very major quest. Okay, and we really don't know what its composition could be. And the problem is that you can't just say that it is made up of certain kinds of particles, because there are all kinds of constraints of how many particles you could have of a given kind. So these could be particles which are very, exotic, meaning that they shouldn't affect our other calculations, but still be present there. So you can't just have black holes, because then where did the black holes come from? And black holes can also be detected. So which is what makes the quest for them so difficult. And every once in a while somebody writes a paper saying that there are some kind of particles, but we still don't know. So maybe you will discover the nature.
So, Kia, back to you. There is, I think, also in the chat box, there is a question from BAK.
So there is Mr. Pallav. Please unmute. Please ask your question, Mr. Pallav.
Anuj, also BAK.
BAK, please ask your question. Who is there? Please
unmute yourself. Maybe they have left.
I'm here. Thank you for the opportunity.
Okay. Yes.
I would like to know what is the minimum size of the exoplanet that JWST can detect. Is it possible to estimate what kind of sizes?
See, what happens is this. Now, one important way of finding exoplanets is through the eclipses that I talked about. So if you remember the diagram, the reduction in light which comes in because of the eclipse is like 1%. And so the 1%, 0.5%, it depends upon the size of the planet. So as time passes, you'll be pushing it as far as it can go. Right? So then gradually, as you understand the JWST calculations much better, so you'll be able to detect smaller and smaller planets. Other thing which I just read it, but I have not read any details at all, is that there's something called direct imaging. Okay, meaning that can you actually get an image of the exoplanet? For that, you have to remove the light of the star. And for that, you use something which is called a coronagraph. Let us suppose that you want to study something close to the sun. You can put a sort of a diaphragm which will cover the image of the sun itself, and which then lets you see the surroundings of the sun. So you could have these kind of techniques to get a direct image. a few direct images have already been obtained using other instruments, but JWST has started getting those too. And so there will be different techniques which are used as time passes, and then you will push the limits as far as they can. So there's no absolute limit on it. It all depends upon the thing, and then you start finding new kinds of exoplanets and so forth.
Thank you very much. One more question. Is it possible to detect the center of the galaxy with the help of JWST?
In principle, yes. Because you see, the thing is that as you see, what was required in the work which I reported here was first near infrared, and that is what JWST, that's the wavelength it works at. Then you need extremely good resolution, so which is also possible with the JWST because it is in space. And then there's no effect of the atmosphere, and you can have very long observations. But I don't know whether there are any technical difficulties in doing it. And you'll of course have to do it over a very long period, because as you see, the orbital period is about 16 years. So which means that you'll need the JWST to be around for a very long time for you to use those kind of observations. But I'm sure that it will be possible.
Thank you. Thank you very much.
Thank you. Professor Bagla, would you like to say a few words in closing?
It was a wonderful talk, and I think particularly the part about JWST and its capabilities, it continues to amaze all of us, and we hope to do amazing science with it and keep on seeing these pretty pictures as well. So thank you, Ajit, for sharing all of this.
So, Kya, before we close, I may just tell Ajit that today happens to be the birthday of Rajesh Kochhar.
Oh, is that right?
Yes. So I got a message from his family that the family was getting together at the birthday of Rajesh Kochhar, and they had actually invited some of us also to join at their house for the Havan and this thing. So in some sense, your talk, Rajesh would have enjoyed your talk immensely.
Yes.
And he has been a close friend of yours also for a long time. So we miss him at our forum because he was a live wire, in his very sharp comments.
He passed away about a year ago, right?
Exactly a year.
Exactly a year ago.
First, I see first death.
Yeah. So we had held a memorial service in his honor, but
yes, I remember that one actually. I did it.
So, Kya, back to you.
Thank you. And now I request Mr. DharamVir to give concluding remarks and vote of thanks.
Well, right at the outset, I'd like to thank Professor Ajit Kembhavi. His lecture was really superb, very fascinating, full of information, motivating. I never heard such a lecture on astronomy. A lot of information was new to
Sir, your voice is interrupted. Hello.
DharamVir, we cannot hear you. Is your connection?
Hello, sir.
Kya, please unmute yourself. Kya, please unmute yourself.
I think their connection
please,
is lost.
Yes, please go now, sir. Please go now.
So, first, I'd like to thank Professor Kembhavi for his mind-blowing lecture. This is the information that we got from him is tremendous. We were not aware of the developments that are taking place in astrophysics or astronomy and cosmology. So we are indeed grateful to him. In fact, we might like to invite him for a physical lecture as situation improves, to interact with the public, students at large. We have been holding lectures at the largest theatre, Tagore Theatre at Chandigarh, and we would certainly be happy and obliged if you could accept our invitation as and when it takes place. Obviously, it will be according to your convenience. I would also like to thank Professor Bagla to join us, who has joined us as guest of honor. Finally, I'd like to thank Professor Grover for bringing both of you together on our platform. And I also like to thank all our audience, especially and audience, in fact, varied from colleges, schools, and universities and research institutions. This was unique in a way. We have very variety of a huge variety of audience. And once again, I thank everyone for attending the lecture, motivating us, and very stimulating discussion. It could have gone on for a couple of hours. The subject is so exciting. Even a child has a question to ask. So thank you very much. And I will ask here to share a few lectures which are coming up in future.
The next lecture is by the director of Wadia Institute of Himalayan Geology. And this lecture again is at the request and initiative of our president, Mr. DharamVir. He wanted a lecture to be organized in the background of what is happening to the Himalayas in Joshimath and so on. And Professor Shailesh Nayak, the director of National Institute of Advanced Studies at Bangalore, who is our advisor, he is be our guest of honor. So I believe our next lecture will be as exciting as today's has been. So please do join us for the next lecture. So back to Kea.
Thank you, Professor Grover, and thanks everyone. So we wind up for today with gratitude and thank you. Namaskar. Bye-bye.
Thank you. Thank you very much. It was my pleasure. Thank you.
Thank you. Bye, everyone.